Welcome back. We're in Lecture 8, Segment 2, the second segment of 3 in this lecture. And what I'd like to do in this segment is just give you a brief introduction to matrix algebra. It sounds a little scary, and this is a little more of a math lecture than most of the lectures I've given so far. But it's necessary to understand the basics of matrix algebra to fully appreciate how these regression coefficients are being estimated sort of simultaneously all at once in one equation, one analysis. So just bear with me and get through this one segment and you'll have a deeper understanding of multiple regression in general. So the important concepts to take away is this is basic algebra. So try to understand just how to add and subtract matrices and how to multiply matrices and take the inverse of a matrix. It's like division. And then you'll notice there are certain types of matrices that are sort of special in statistics. And you've already seen them in doing examples in R. So a correlation matrix is sort of a special matrix. And the unstandardized version of that is the variance-covariance matrix. It's sort of special in statistics. So having a little bit of an appreciation for matrix algebra helps to understand where some of the numbers are coming from, particularly when we do things like multiple regression. So let's start out real basic. What is a matrix? Well, you've seen this in the analysis we've done in R. A matrix is like a data frame in R. It just has rows and columns. And we always refer to the rows first and the columns second. So rows, columns, RC, because matrix algebra is really cool. RC, rows, columns, really cool. So it's just a rectangular table, known or unknown numbers. Here I just made up some numbers. The order is given by number of rows, number of columns, RC. So this is a 4x2 matrix. If I want to take the transpose of a matrix, that's just converting the columns into rows. So you may have done this in maybe Microsoft Excel or some other spreadsheet type of software. Just transpose a matrix. So here I've taken the transpose of M. I've just taken the first column and made it the first row. Very simple. Two matrices can be added or subtracted if they are of the same size or same order. So here's a new matrix N, and what we want to do is just add matrix M and N. And since they're the same order, they're both 4x2 matrices, I can add them together by just adding each cell. So matrix M, row 1, column 1 is entry is 1. 1 plus 2 is 3, and so on. So matrix addition and subtraction is very simple. Pretty straightforward. Multiplication is a little bit more complicated, but not too much if you just take it slowly. One thing you have to know for multiplication is in order to multiply two matrices, they have to be what's called conformable. So the number of columns in the first matrix has to equal the number of rows in the second matrix. It's best to just look at an example of this. So since M and N, the two matrices I was working with for addition and subtraction, since they're the same size, what I'm going to do is take the transpose of M, and then they'll be conformable for multiplication. Because they were both 4x2. If I take the transpose of M, then I've got a 2x4. So if I multiply a 2x4 times a 4x2, then I'll get a 2x2. I may be going too fast. Let's look at this. So I'll get a new matrix R by multiplying the transpose of M times N. So I took the transpose of M, and here's that original matrix N. And the way we end up with this result matrix, or the product R, is we go across the row of the first matrix, first row of the first matrix, and down the first column of the second matrix. taking the product and summing. So if I take 1 times 2, that's 2, plus 5 times 4 is 20, 22. 3 times 1 is 3, so now we're up to 25. 4 times 3 is 12, and that gives us 37. Okay, so what I did is I just went across the first row and down the first column for each entry, multiplying, and then for each product, summing it with the next product. So it was 1 times 2 plus 5 times 4 plus 3 times 1 plus 4 times 3 gives me 37. A way to do this, sometimes this helped me when I first learned it, is to sort of take an example like this and work backwards from the product. So how do we get 37? Well, 37 is row 1, column 1 of the product, so that means it's row 1, column 1. Likewise, 38 is row 1, column 2, so it's row 1, column 2. That's stated more explicitly in the previous slide, but I think it's easier to just show it. And if this is new to you, you might want to work through that example a couple times, or try other examples. Now I want to move to talking about sort of special types of matrices. So you've seen examples like this. So a square matrix has the same number of rows and columns. So here's an example just with some random numbers thrown in. And you've also seen examples like this, square symmetric matrices. So the correlation matrix is a good example of this, where it's square, so the number of rows equals the number of columns, but you'll also see that the entries below the diagonal are symmetric with the entries above the diagonal. We'll also refer to a special kind of matrix called a diagonal matrix. That means it only has entries in the diagonal. All the off diagonals are zeros. So that's a special case of a square diagonal matrix. And finally, the inverse of a matrix is analogous to taking the reciprocal or inverting a regular scalar number. So, for example, the inverse of 2 is a half, and the product of 2 and a half is 1. The product of 2 times 1/2, to be clear, is 1. Inverses only exist for certain types of matrices, so they only exist for square matrices, and then sometimes you can't even invert square matrices. And that sometimes results in problems in multivariate procedures, which we'll get to. But we want to be able to take the inverse so that if we take a matrix D and multiply it times the inverse of D, we'll wind up with the identity matrix, which is like in scalars taking 2 times the inverse of 2, a half, with getting the result 1. And here's the identity matrix. Just one more sort of tricky thing in matrix algebra, and then we'll go on to sort of a cool example, is the determinant. And the determinant is just getting a scalar number out of a matrix by taking the product of the diagonals relative to the product of the off diagonals. So in a 2 by 2 matrix, for example, it would be entry A11 times entry A22, the product of the diagonals, minus the product of the off diagonals. This will become important as we look at some of the output in R. And just one other thing I'd like to mention, and we've done this in R, is looking at row vectors and column vectors. So a vector is just either one row or one column. So I may refer to a R, for example, here as a row vector, and C, for example, here as a column vector. Again, understanding these basics, this may feel a little dry relative to some of the other segments, but understanding these basics will help us understand how the regression coefficients are calculated in multiple regression. And to show you, just sort of give you a glimpse of that, we'll practice some of this matrix algebra right now in going from what I'll call a raw data matrix to a correlation matrix in just 10 steps. That's it, 10 steps. And then we're done with this intro to matrix algebra. Okay, so imagine we have this, what I'm calling a raw data matrix. So you can imagine, like some of our examples in R, each row represents an individual subject in, say, an experiment or a study, and each column represents their scores on different variables. So this matrix is matrix X for raw scores, and it's n by p, n for number of subjects, and p is the number of variables, or number of measures. And I just came up with some random numbers. You could think of these as maybe like scores on a Likert scale of 1 to 7. And there's 3 variables. So those are the raw data matrix, the subjects and their scores. We could use matrix algebra to calculate the correlation coefficients between these 3 measures. So are these scores in column 1, are they correlated with these scores in column 2, and so on with column 3? We did that in descriptive statistics, and we just did it by employing basic algebra. We're doing the same thing here, but we're going to do it in matrix form. And that's actually what's happening under the hood, so to speak, in R. So the first thing I'm going to do is pre-multiply this data matrix by a row vector of 1s. And what that'll do is it'll give me a row vector of sums. So this is just like adding up all the numbers in a column. And what we're going to do here is get the means, right? But to be fancy and do it in matrix algebra terms, we're going to pre-multiply by a row vector of 1s. So what I do is take this and multiply it by this first column, then do it again for the second column, and I'd wind up with just getting the sums. And I'll call that a row vector of sums. We can then get a row vector of means just by taking that previous product, the row vector of sums, and multiplying by the inverse of n. The idea is you're just dividing by n, right? This is how we got the means. So now we have the means for each column, but represented in a row vector. Now I can create a whole matrix of means. So I want this matrix to be of the same size as the original data matrix. So what I'm doing is pre-multiplying by a column vector of 1s. Another just fancy step to create this big matrix that gives me each column a mean. What that allows me to do is get a matrix of deviation scores. Remember, we did this exact same thing, just employing basic everyday algebra. Now we're doing it in matrix form. So now I have my original data matrix, I have my matrix of means, and if I just subtract them, then I get a matrix of deviation scores. So this is like way back in descriptive statistics, where we did that example with Jeremy Lin's basketball points per game. We calculated deviation scores. Right? That's exactly what we're doing here, but we're doing it all in one big step with matrices. So now I have a matrix of deviation scores. What's really cool about this, and this is the part where I actually think matrix algebra gets pretty neat, because this is where it's sort of special to statistics, is from that matrix of deviation scores, we can get sum of squares and sum of cross products. And remember, we did this by hand when we did descriptive statistics and correlations, but now if we just take that matrix of deviation scores and pre-multiply it by its own transpose. So I've just taken that matrix of deviation scores, transposed it, I'm going to multiply them. Then what I get is really cool. It's a matrix that represents the sum of squares and the sum of cross products. So in the diagonal, we have the sum of squares, because what I'm doing to get the diagonal entries, how do I get this entry 10.4? Well, it's in the product, it's row 1, column 1. So I would have to look at row 1, column 1. That's just for the first variable. I'm taking each deviation score and I'm multiplying it by itself and then summing all the products, right? That's how matrix multiplication works. So it's the sum of squared deviation scores. So in the diagonals, I get sum of squares. And in the off diagonals, I get sum of cross products. It's pretty cool. From there, I can get the variance covariance matrix. Remember, variance is just sum of squares divided by n, if we're doing descriptive, and that's all we're doing here. And covariance was just sum of cross products divided by n. So again, I'm going to be fancy, and I'm going to multiply by the inverse of n. That's just dividing by n. And now I have a variance covariance matrix. So in the diagonals, I have variance. In the off diagonals, I have covariance. So now you're smelling it. We're getting close. We're almost at the correlation matrix. All we have to do is take a diagonal matrix that has the standard deviations. So that's just the square root of the diagonal entries of the variance covariance matrix. And if we pre and post multiply that by the variance covariance matrix, that gives us the correlation matrix. We're just standardizing the variances to be 1 and the covariances to fall between -1 and +1, essentially to be correlations. So there we went from the raw data to the variance covariance matrix and the correlation matrix, all using this new skill, matrix algebra. And that didn't take too long, 15 minutes. Pretty easy. Okay, so to wrap up this segment, this may have been new for you. If so, you might want to review it a couple times to make sure you understand how to add, subtract, multiply, take the inverse, and maybe go through that example again to make sure you understand how we can get from raw data to a correlation matrix just using matrix algebra. Once you have those basic skills down, then we can apply that to the multiple regression example to see how we get those multiple regression coefficients estimated all simultaneously in one analysis in multiple regression.